It was in our last lecture that we explored this colliding of two worlds between the algebraists, who were trying to handle problems where we were looking for missing solutions, and the geometricians, where we were looking for shapes and trying to describe numbers in terms of quantities and relationships. And when we collided both of these from René Descartes' invention of the coordinate plane, we really began to see that these were just two different ways of modeling the same ideas. We could look at shapes as being a relationship between a height and a distance along a horizontal axis, or we could look at it as being solutions to a number problem. Now, today we're going to be playing around a little bit more with the idea of circles, and circles have been one of the most complexing shapes that mankind has ever gotten the opportunity to play with. I mean, if you think about circles, they're not as cut and dry as you might think. They're simple to create and they pop up all around the natural world. You can look at flowers that seem to open in the shape of circles. It was believed for a long time that planets and moons and celestial bodies would orbit in the shape of circles. The sun appears as a circle. The earth itself appears as a circle if you zoom out far enough. And so you've got this circle that continues to just challenge us from the rest of nature, which so bubbles appear in circles and spheres. Why? Where is this pattern that continues to emerge? And so man would study this, and women would study this to find all of the commonalities, the underlying truth, the logic that connected all of this. And the moment that we were able to put equations behind it, we really got a completely different perspective for where circles are coming from, how we can describe them, and how we can to simplify them down into just bite-sized pieces of information. So let's talk about circles for a little bit, but before we do, we need to get a little bit more understanding of this coordinate plane that René Descartes came up with. And so let's do a little bit of an exploration with parabolas, and we'll explore with parabolas, these quadratics. We'll explore with this because we've been playing with it for a while, and we'll build our way up to circles and see that they're oddly connected and similar. So here's my first question for you. How would we graph y equals x cubed? Well, just as a little refresher, we would start by sketching out a coordinate plane. So we could take our pen, we could say y equals x squared could be thought of as all of the x values, horizontal distances, that if I put them in as x, would result in vertical distances y. So for example, I could put in a distance of 0. I could go 0 over in my horizontal, and then that would mean that I would put in 0 for my x, that would square to be 0, and that would give me y equals 0. So I would have 0 and 0 as a point. So there'd be one set of solutions, one ordered pair, 0, 0. I could then say, well, what if I went over to the right one step? I've gone a distance of 1, whatever that 1 may be. Then I would square that, and I would say, okay, here we are. This would be 1, 1. This would be what happens when I put in 1 and I get out 1 after squaring it. I could put in a distance of 2, and 2 would then result in a distance of 4, 1, 2, 3, and then 4. And so I would get another point up here. Similarly, I could say, well, what if I took a step towards the negative? I took a negative direction step, and I squared that -1. That'd be -1 times -1 gets me a +1. And then I could say, well, if I took 2 steps towards the negative, then I would square that to get me a +4. And so I've got a little bit of symmetry, this picture, this U shape that emerges that we would call a parabola. And in fact, what I've done here is not only sketched out the shape that is hidden by this equation, but I have another shape that captures every possible square I could ever build. Isn't that kind of interesting? After all, I have x squared here, so that means any square, any number I start with, if I tried to make it into a square, I would get some kind of size, my output y, my size, that would result after I was trying to put in some kind of side length or starting value of x. So any side length x is going to get me the size of my square, which we call y, or x squared. Kind of interesting. Now, what if I just want to play like the algebraists do, and I want to change some of the numbers here? My question is, what happens if I make x get a little bit bigger by 2? What would happen? Well, we could imagine that would change my x values for sure before they would be turned into y values. But is that going to be a shift of my parabola to the right? Is it going to bring it towards the positive x? Is it going to be something different? And so let me show you a really cool online tool. This online tool is called Geogebra. And so if you go to Geogebra, let's go ahead and pull it up here. What I've got graphed is the parabola that you would expect to see from what we were discussing before. So I've typed in this f of x equals x squared. And this is a notation that you don't have to be familiar with quite yet, but what this really just means is I have a function, or I've got some kind of graph that I'm going to label f. And you can see that it's got a little green f right here to say that this is what I'm calling it. I'm calling my green f to help us just keep track of it. So I've got my green graph f, and it is going to be equal to x squared. So for our purposes right now, you can imagine that this is y equals x squared. And I'm curious about what happens if I make this into an x plus 2. So here's your moment to take a second and make a quick guess. What do you think is going to happen if I add 2 to x? Is that going to cause my number 0 here to shift over to the 2? Something else going to happen. Let's try it out. I'm going to shade it in. Now that's surprising. Why is it that if I add 2 to x, it seems like my entire parabola shifts so that now it's over here at this -2. That might have been a little bit, we would expect that adding 2 would cause me to go towards the positive direction. What's happening here? Well, let's see if we can take a step back into the meaning. Let's take one of these numbers, let's follow it through the journey. Let's imagine that I put in this -2 into my little blue graph over here. So I put in -2 for x. -2 plus 2 would be a 0. 0 squared would be a 0, and that's why if I put in -2 into my blue graph, I get 0, 0. Oh, so that's really what's happening. If I've shifted everything over 2 by adding 2, what I'm really causing to happen is it's treating all of these numbers as if they were 2 bigger than they actually are. So the other way of thinking about it is that by adding 2, I'm really allowing for numbers that are 2 lower to pose as numbers that are the 2 higher than themselves. Interesting. Okay, so really, let's see what happens if that holds through if I try it for x minus 2. Okay, so let's maybe call this one h. We'll call this one h, and we'll say that this is going to be x minus 2 squared. Oh, there we have it. That's our purple. So if I take away the blue, if I took away 2 from the x, that's really shifting it over to the positive 2. It's like I took everything from my picture and I just moved it over. Interesting. Well, I'll show you that it's actually about us changing our perspective. So let's go back over here to our notes, and I want to show you here what's exactly happening. So let's start with our original picture of our parabola. It looks something a little bit like this. There we are. And we said that we were trying to figure out what happens when instead of y equals x squared, I'm now looking at y equals x plus 2 squared. Well, what I would interpret this as before I had drawn a picture is that I'm taking my x values and I'm adding 2 to it. So if my x value was originally 0, in other words 0 steps over, then that would now be 2 steps over. So I'm taking my 0 steps and I'm moving it to 2 steps. And I'm taking my 1 step and I'm moving it to 3 steps. I'm kind of growing my steps by that. Well, what that means is that I'm really shifting this axis. I'm shifting the whole picture. I'm shifting my ceiling. What I thought was 1 step away from the corner of my room is now 3 steps away from the corner of the room. I'm moving my entire ceiling away. So we can see all of this. This really is just our changing our perspective. We're moving it not 1 over, but 2 over. So really when we're adding to our x values, we're really shifting our entire coordinate system. The adding is to the x's, the x-axis. It doesn't have anything to do with our pictures. Our pictures are just along for the ride. Our graphs are just looking like they're being shifted, when in fact it's really us shifting our entire coordinate system. Kind of crazy. So similarly, we could say, okay, well, what's it going to be if I have y equals x minus 2 squared? Okay, well, let's go back to where we had it originally. So we had it back where it was in the center. This was our y equals x squared. And now I'm saying that I want to take each of those x values on my axis and I want to take them 2 towards the negative. Okay, let's do that. We're going to shift it 1 to the negative and then 2 to the negative, and I'll drop it there. So again, it looks like I've taken my entire parabola and I've moved it over to the side, but really what I've taken is the coordinate system underneath it and moved that away. That's really interesting. Okay, let's see if that works out in the computer on Geogebra. Let's go back over to Geogebra and test our theory. So we're now going to see what happens if I take x minus 2 squared. So I'm trying to see what happens if I shift it, and I'm expecting that by grabbing this system, this entire coordinate system, and moving it 2 to the left, it's going to make my graph look like it's moving 2 to the right. Let's find out. there it is. So the idea of saying I'm subtracting 2 isn't about moving my graph, it's about moving my coordinate system. A fun little discovery. Okay, let's see if we can generalize that idea for some of these other ones. So we found out some notes. We found out that this is going to have the exact same shape as this one because I'm still squaring things, but if I grow my x's by a certain amount, that really just means I'm shifting the coordinate system underneath the picture over. Okay, so now I can very easily say that the graph for the second one is the same parabola. It's just that I'm going to shift all of my x values to the right 2, which makes it look like the graph has moved to the left 2. Okay, however you want to think about it, it's all the exact same idea. But it's going to look a little something like that for the second picture. And the third one, just to copy what we were talking about, is that if I've moved my coordinate system, I grab my coordinate system and I've moved it over to the left, it's going to make my picture look like it moved to the right. Kind of crazy there. Now, what about something like this? What if I want the exact same relationship, but now I want to add 2 to the y? Should we try it? Okay, let's try it. Let's put it back into GeoGebra. So now I'm going to have something like y, I think it was plus 2. Let's see, y plus 2 equals x squared. And we'll take away everything else. Okay, so we've got the same idea. If I add 2 to my y, it's as if I'm moving my coordinate system up, and it looks like I'm dropping my picture down. Okay, so that's the same idea. So if I add 2 to my y, it looks like I'm shifting that entire thing up and I'm leaving the picture where it was. So that's going to look like the picture dropped. Now I'll show you how we're used to seeing something like this. How we're used to seeing something like this in an algebra class is where we solve for y first. So we say y equals x squared minus 2. Let's see if this has the same, or at least a relatable meaning. All right, so we make a parabola. That's exactly what the x squared means, no problem. And then it looks like we take that number that was going to be our height, and we need to make that height smaller before we plot it. Oh, that would make sense, because then if I put in, for example, 0 for x, that'd be 0 squared, and then instead of plotting my little 0 point here, I would need to shift it down 2 because I'm subtracting 2, and then that would really be my y. It would be right down here. So however you want to view it, whether we're grabbing the coordinate plane and shifting it down, or we're viewing the graph and we're pulling that down, or we're moving things across the equation to view it, it's the same idea, it's just a different perspective. Fun little exercise. But I kind of like this idea here first of saying if I'm going to subtract 2 from y, that means that I'm moving my entire coordinate system down 2, which means that it looks like my picture went up 2. So I can really easily say that that next graph is going to be just like this. It's going to be the exact same shape, width, and pattern as my original parabola, but it's going to look like it got shifted up. And if that feels a little bit odd, just solve out for y. That'd be y equals x squared plus 2. And so what that says in a story is before you find your height, find a parabola and then bring it up by 2. So keep track of that one when we're playing around. It's going to help us when we're dealing with more complicated equations like circles. Okay, so let's talk a little bit about circles. Now that we've kind of got a little bit more familiarity with our standard coordinate system, what does it mean to be a circle? Well, we alluded to this a little bit last time. We said that a circle is really all points that are a certain distance away from a center. That's the way you can think of the definition of a circle. So if you ever want to draw a circle, grab a string, grab a pencil, grab your friend, have something that anchors you down in a center, and then run around that center to form a circle. So for example, even if you look here at my pen, if I wanted to create a circle, I could just keep my top hand the same, and I could go all the way around, and I could sketch that as being a circle. Okay, so what's the standard form of the equation of a circle? Well, we know that really in this circle, if I talk about having my coordinate system, and I start to sketch out my circle, then I'm going to start with some kind of little radius here, we call it r, and that because my setup talks about going left and right and up and down, I can always reference this back to a triangle. And that if I want to look at this at any given point as taking that pen and spinning it around, or taking that radius and spinning it around, really that's just another triangle. And all of these are triangles. Circles are really just triangles in disguise. There are a whole bunch of these small triangles that are all related because they have the exact same hypotenuse. Okay, so we get circles and circles and circles and circles, or triangles and triangles, triangles and triangles, and if I want to capture all of those triangles together, they all form a circle. So circle is really a way of saying all possible triangles whose hypotenuse is a certain length. That's another way of saying, or another way of changing our perspective to say that circles are really just a whole bunch of hidden right triangles. Okay, how does that help us? Well, it helps us when we're trying to describe the behavior, the essence where these circles come from. We could talk about them as being all of the possible different triangles that make them up. So for example, if a triangle, a right triangle, always has to follow the Pythagorean theorem of a squared plus b squared equals c squared, and I know that my radius, my little radius here, is my c squared is always going to be a certain number, then what I can do is I can say that my a squared is just going to be the other side of my triangle, possibly my x, the one that goes along in the x-axis, so it could be my x side of my triangle, okay? That'd be x squared. My b side would be the one that goes in the up direction of my triangle, in other words, my y direction of my triangle, so that'd be y squared. And then I would have c squared. C squared is just some number, whatever radius I wanted to start off with. So if you wanted to, you could even just call this r squared. It could be some number that we create. So if I wanted to know what's the circle whose radius is 10 units long, no problem. That's going to be the equation x squared plus y squared equals 10 squared, which would be able to be also written as x squared plus y squared equals 100. This would be all of the numbers that work for this solution would actually give you the outside picture of this triangle. It would look just like this. Now in drawing, I used to draw quite a lot, and so in drawing what they always teach you is to start with construction lines, and that's kind of what we did in this exploration, is we started with our construction lines of saying, well, how would I think about my circle? How would I want to sketch out and make sure that my circle is well organized? How would I want to describe the circle to somebody else? And you can put in all of the supporting logic of saying that circles can come from right triangles, and that right triangles are thought of using the Pythagorean theorem. But at the very end of your picture, when you're ready to make it pretty, you erase all those construction lines so that you just get the end result. And that's really what we've done here, is we started with all of our thoughts on the paper, and then I went to saying, really? A circle of radius 10 is just like this. Now, before we talk about the standard form of the equation, before we finish talking about the standard form of the equation, it's important that we capture what we did in the introduction of this lesson. And that is that we don't just need to have circles whose center is right here at the origin. We could have circles that are centered anywhere. I could draw a circle on the screen that's just down here at the bottom left. I could draw another, or bottom right. I could draw another one that's over here at the top right. So we need to talk about how we would move this circle around. Well, that's no problem. We were just talking about how we were shifting the axis before. We could write the standard form of this circle as being affecting our x so that our x moves over a certain amount. So if I wanted the center to move 2 steps to the right, then really what I want to do is take all of my x values on my axis and shift them 2 values to the left. Okay, so that'd be like if I was trying to move my axis over, then the certain number of steps would be, let's call it h. So I'll say I have h steps I want to move it over. I would just need to subtract that number from x. That would move all of the coordinate system over, and it would make it look like my circle started somewhere else. All right, so x minus h, and then squared, right? Whatever I do to the x just affects it, and then I'll square it like I did with the parabola. Okay, let's do it for y. And then I would say, if I wanted to have my y, the center go up 2, then really what I want to have is my coordinate axis go down 2. So I would need to just subtract the number of steps I wanted from y, and that would cause it to go look like it had gone up that certain amount. Okay, perfect. And then what about on the far right-hand side of the equation? Oh, the right-hand side was just my radius, right? So I'll always put that as just my radius squared. And this is where you get your standard form of an equation of a circle. It has all of the information you would need to be able to draw a circle anywhere in space that you would ever want, that has all of the information that a circle has, which is it has a center and it has a radius. Those are the 2 pieces of information you need for a circle. Now, after all that exploration, let's see how we might tackle some problems that allow us, the algebraists, to help to interface with the geometricians, those who are just simply wanting to draw circles at different places that have different radii. So, for example, let's go ahead and take a look here. There is a video that you can look at through your text just as a reminder, but for right now, I don't think we're going to need it. So let's try to find the standard form of an equation of a circle whose center is at 2, 3, and whose radius is 6. Now that's a lot to kind of think of, and I've got a lot of numbers and letters popping through my head. Let's just sketch this out for a moment. So here's my sketch out. I'm going to look at a center of 2, 3. That means, okay, I've got 1, 2 steps to the right, and I need to go 3 steps up. 1, 2, 3 steps up. So this is going to be where I put a point, and that point is my center. Okay, no problem. The radius is 6. Okay, so let's see. That would be a radius like 1, 2, 3, 4, 5, 6. Okay, 6. So this is my construction line of a radius, is just like this, and this would be going off in many different directions all over the paper. And I could connect all of that to get the picture of a circle. It's going to interfere here and here. Oh, we'll need to bow that out a little bit more, make it look like a radius. Okay, that looks not horrible. Okay, and then we could erase all of our construction lines. So this is a circle who has a center and a certain radius. Okay, and I want to try to find the equation for that. No problem. Here's how we could do it. Now that we went through all of this work up here, let's just take it and use it. I have x minus h. What's h? H was my number of steps over to my center. Okay, so I went step 1, I went step 2. Okay, x minus 2, no problem. Squared. What if okay, my center is 3 high though. 1, 2, 3 high. So it would be as if I had taken my coordinate system and I had shifted it down 3. That's why when I keep going through my equation, it's x minus 3 squared. It's like I started off at the beginning and I shifted my coordinate system over, and then I shifted it down so that it looked like my center had gone to the right and up. Okay, great. What about the radius? The radius would be 6, and so I'd need to put that over here. Oh, but remember that these are all relating like we had a triangle, so this is really c squared. Okay, perfect. So I could write all of this as saying x minus 2 squared plus y minus 3 squared equals 36. This should be the equation of a circle. Should we test it? Let's go back over to Geogebra. All right, we'll clear all these away. So I have x minus 2 squared. Let's look at how this transforms. This is pretty fun. We've got y minus 3, because I needed to go up 3. Okay, y minus 3 quantity squared. Okay, and then that equals 6 squared, or 36. And there's our circle. Isn't that just kind of fun? So we can actually look at all of these different points, every single point on here, if we wanted to plot one. Let's try to plot some points. All of these points here, like for example what A is just a point that actually meets all the conditions that we had for making our circle. It's a point that falls on our circle. Should we see if that's true? Okay, well, let's see. I want to do, how can I play on this? I had my center. My center was at, we said 2, 3. This is my center of my circle. The center should always be 6 units away from the edge of the circle. Let's see if that's true. I go 1, 2, 3, 4, 5, and 6. Oh, there we are. So it's 6 units away over there. Let's see, 1, 2, 3, 4, 5, and 6. It's 6 units away there. What about something on the diagonal? Oh, that's kind of fun. Let's choose something like, oh, is there anything that intersects nicely? Maybe not. Let's choose something here and see if we can show its value. So let's show the value. Ooh, crazy number. So without even doing any math, what I can say is that if I looked at the distance between this point right here, this point D, I looked at the distance between D and the distance of B, I should be able to prove that that is 6 units away. And in fact, I can, because this is a point on my circle. My circle was made using triangles, where triangles were saying I'm going to go over a certain amount from my center and down or up. And so if I go over and I go down and I use both of those measurements and I form a right triangle, I will get back to 6. Super crazy that you can do all of this different work, and now we don't even have to worry about having found crazy long numbers like we have here. And these are all over the circle, right? You have points that are popping up everywhere. There's so many different ways that you could have found a solution to that equation. There's another one. Oh, what's the one at the top? The one at the top should be pretty easy. It would be 6 away going straight up. So that would be 1, 2, 3, 4, 5, 6. Sure enough, that's going to be at 2, 9. We can find that one here. We'll put that in. 2, 9. Give me 2, 9. There it is. So here you are. The equation for every single solution you could possibly have to our original question, every single triangle you could possibly form whose hypotenuse is 6 units long, gives you a circle, gives you an outline, a sketch that is a circle. All right. So let's see what we can do to solve some of these other puzzles. Find a standard format of a circle whose center is at -6, 2. Okay. And it passes through the point 4, 2. Ooh, now that's a fun riddle. Let's play. We are going to make a coordinate system. I am going to put the center at -6, 2. That's -1, 2, 3, 4, 5, and 6. -6. I need to go 2 high, 1 and 2. All right, so this is where the center is at. I can start to describe the standard form of my circle using an equation, right? So that would be x 1, 2, 3, 4, 5, 6 units to the left must have happened from the coordinate system going 6 units to the right. Okay, so that's as if I went and grew each of these by 6. So notice the kind of parallels here. You can either think of it as saying I have x minus my center being -6. So x minus -6 is how we were thinking about it before. Let's take a look up here. Right? X minus h, where h was my center. And so here, if my center is -6, I could look at it as x minus a -6. Or you could go back and do the original logic again, which is to say that if my center is 6 to the left, that must have happened from my coordinate system getting grown 6 in the x direction. All right, so we got the first part. It's at 6, 2, so that would be 2 high, which happens from me dropping my y down 2, or by taking my number 2 and plugging it into my original formula, right? Y minus k, where k is my center, so I could put it in as k. That'd be y minus 2, and I'll square that. And then I have equals my radius squared. What's my radius? I don't have a radius. I need a radius. Okay, let's make a radius. Okay, where's this point? I know this point is on my circle, so let's do that. 1, 2, 3, 4, and then I'm going to go to 1, 2, up 2. Here we are. Oh, well, isn't that my radius? Isn't my radius going to be wherever I go from my center here, and I go all the way across to one point on my circle? Isn't that going to be my radius? How far would that be? That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That'd be 10 units away. So that'd be 10 units away from my radius, and I need to make sure I square it so that I keep track of the fact that this is all just triangles I'm using to sketch it out and construct it with. Okay, well, I think that's about it. X plus 6 squared plus y minus 2 squared equals 100. Very nicely done. What if I didn't have it perfectly in line? What if it was a little bit off? Okay, let's play. Let's make this a little bit harder. What if instead, so we'll give ourselves a new question. I said instead, it had a center at -6, 2, but it passed through a point, and the point was at 4, 4. There we go. That's a little bit harder. Do we need to draw out the picture anymore? Can we just maybe work with what we have? Well, I need to find the distance between the center and the point. I have a distance formula. My distance formula back from when I was studying with my coordinate system and my lines before. How did the distance formula go? Oh, it was the distance formula was if I had a point and I wanted to get to another point, then I just looked at how much I needed to go over, how much I needed to go up, and I made my triangle. Oh, it's the right triangle. It's the exact same idea as everything else we've been playing with. So let's just use this idea of, again, this right triangle to get my radius. Okay, so I'm trying to go from the center to this point. That would be, how far is my x direction? That would be the absolute value of -6 minus 4, right? Because I use absolute values when I'm finding my distance. So that's absolute value of -6 minus 4 equals 10. And then I have the absolute value of 2 minus 4. 2 minus 4 gets me absolute value of -2 equals 2. Okay, and then this would be the other side of my triangle. Okay, so that would be what, 10 squared plus 2 squared equals c squared, Pythagorean theorem. A squared plus b squared equals c squared. That would get me what, 10 squared is 100 plus 2 squared is 4, so that's 104. And so all in all, I could say that my c value is equal to the square root of 104. Because if c squared is 104, then c alone must be the square root of 104. No problem. Okay, but we did find c. In other words, we did find our radius. So maybe I'll just call it my radius from now on. This was my radius. Okay, so I found the radius. I have a center. I should have everything I need for the equation of my circle. X minus the center, so that'd be x minus -6, x minus -6 squared, plus y minus my center would be 2, y minus 2 squared, equals r squared. R squared is square root of 104 squared, so square root squared would just be 104. I think that's it. That would be, we could simplify it a bit, but that'd be x plus 6 squared plus y minus 2 squared equals 104. There we go, 3 lines of work, and we're able to find the equation of a circle just based on knowing where its center is and knowing where another point is. What about this one? Find the standard form of an equation of a circle that contains endpoints of a diameter at blah and blah. Okay, that's too much. Let's put some pictures on the paper. Let's do our coordinate system. I have 2 points, -4, 3, so that's -1, 2, 3, and 4, and then 3, 1, 2, and 3. So that's going to be -4, 3 right there. I have another one at 2, 1, so that'd be 2, 1 right there. Now it says, find the standard form of an equation of a circle. So here's how I would start to break down these difficult problems. Standard form of an equation of a circle. That means that somehow, some way, where I'm going to have x minus h squared plus y minus k squared equals r squared popping up at some point in this solution. All right, so find the standard form of the equation of the circle. Got that right there. That contains endpoints of a diameter at here and here. Ooh. So a few things I need. First thing I need to have the center, and I don't have the center right now. Essentially, my picture is going to look something like this when I'm all the way through. Those are the endpoints of a diameter. Diameter goes all the way across a circle. I need to find the middle. I don't know where the middle is. But we played around with that when we were working through the coordinate planes. The midpoint formula, remember the midpoint formula? If you don't, here's what it is. It's saying that what I'm going to try to do is if I have -4 and 2, and I would like to figure out the halfway mark, the halfway point between them, I could just look at the average of those two. I could look at the middle of the two. Okay, so that would be -4 plus 2 divided by 2, and that would be the middle between my x values. Okay, what about for my y value? That would be the middle between my y values. So that would be 3 plus 1 divided by 2. Let's see if that worked. -4 plus 2 is -2, divided by 2 is -1, and then 3 plus 1 is 4, divided by 2 is 2, and there we have it. It's about at -1, 2. That seems pretty good with my picture, not too far off. So I've got my center. In other words, I have my h value, and I have my k value. What about my radius? Do I have a radius? Well, we have two different options here. We could find the distance between the center and one of these points. No problem. I have the center. It's right there. I have a point. This one right here. I could even use this point over here. Find the distance between any of those, between the center and either of those 2 points, and you have the radius. That's what it means. I'll tell you another way that I think is kind of interesting. What if I accidentally made a mistake for this problem? In engineering, there's a phrase that says you always measure from the baseline, and what that means is that if you're ever trying to measure something, you'd never try to measure from a measurement. You always try to measure from the place you started, what we would call the baseline. And you do that so that even if you made a mistake halfway through, you can hopefully correct that by going back and starting with the same information you had. What I want to do in this problem is something similar. I want to say that maybe I'll just find the distance between the 2 points I know are correct, and I'll break that in half. So in other words, I'll find the length of the diameter, and I'll put that in half so that I could get the length of the radius. Oh, all right, let's try that one out. So this is a choice I'm making. You could do this one, you could do the other way you want. There's not a right, there's not a wrong. So let's play. The distance between these 2 points would be, well, the distance between the x values. That would be negative 4 plus 2 squared plus the absolute value of 3 minus 1 squared. Let me see if I did that right. Hold on. Negative 4 minus 2. Nope, I need to find the distance between them. Minus 2. There it is. Negative 4 minus 2 squared, and then 3 minus 1 squared. Good. The difference, and then I make the absolute value because that's how I find distance, and I make sure that everything plays out nice. What did I really do here in terms of this equation? Where did this equation come from again? It's another triangle. Negative 4 minus 2 squared is the length between negative 4 and 2. It's this length right here. What is 3 minus 1? That's this height right here. And so long as those are both made positive, what I've formed is a right triangle. If I square them and add them together, that's going to give me my diameter squared. Okay, so let's do that. Negative 4 minus 2 equals negative 6. Made positive is 6. And then squared would be 36. All right, so it's 36 plus 3 minus 2 is 2. Squared is 4. And that would be my diameter squared. So 36 plus 4 gets me 40. That gets me my diameter squared. I need to square root that. So that would be a square root of 40 equals my diameter. No problem. And that means then that my radius is half of that. So my radius is the square root of 40 over 2. Now we could simplify that out a little bit, because square root of 40, you could pull you could factor out a 4, and then the square root of that would become a 2. So really you could think of this as 2 root 10 over 2, which you could simplify to just the square root of 10. There we have it. So we have the square root of 10, and that is my radius. And so I think I have everything I need for my original equation. I have my h, I have my k, and I have my r. So let's put that all in. I have x minus h. X minus h would be x minus a negative 1 is x plus 1 squared, plus y minus k, that'd be y minus 2 squared, equals r squared. R is square root of 10, so r squared would be 10. And that's going to be the standard form of my equation for a circle whose endpoints of the diameter are located at these 2 points. So we're just playing, we're pulling it all back, and we're really anchoring in our skill set and our perspective for saying, I can just look at triangles, right triangles, any given time, whether I want to talk about circles, whether I want to talk about distances, whether or not I want to talk about midpoints. Well, midpoints is really just us taking those two and then dividing it in half. So essentially we're looking for where is the middle of those two values. Kind of fun. All right. Find the center and radius and sketch the graph of the circle, all of this. Ooh, does it have any intercepts? First thing, is that a circle? That doesn't look anything like a circle. Well, let's play. Let's see if it is a circle. Maybe it's a typo. Let's play. What could I do? What could I do? What could I do? Well, I know that I want to eventually get it into something that looks like this. X minus h squared plus y minus k squared equals r squared. I want to get it to this. It's nowhere close right now. Let's simplify it up a little bit. So 2x minus 1 over 2, how could I think of that? I could think of that as being 2x minus 1, and then I guess I could divide each of them by 2. Okay. I don't know what I'm doing here. We're just playing. Minus 36 equals negative y squared. I don't want it to be a negative y squared. I want it to be a positive something affecting y squared. Okay, well, my parentheses are simplifying a little bit. Okay, that worked. 2x divided by 2 gets me just x. That works fine. Minus 1/2. That's fine. That looks like x minus h. It just means h is 1/2. Okay, that's working fine. Minus number. Am I supposed to have a minus number? No, I'm supposed to have plus my y expression. So let's add 36 to both sides and get rid of my 36 on the left. So that gets me equals negative y squared plus 36. That works. I need to get my x's and my y's on the same side of the equation. So let's try to add y squared to both sides. That would give me x minus 1/2 squared plus y squared equals 36. Okay, we're closer. I'd really like to know what k is. Well, If I just have y alone, that means that I haven't subtracted anything from it. Oh, so that's just x minus 1/2 squared plus y minus 0 squared? I guess you could say plus 0. Minus 0 plus 0 really doesn't matter. Equals 36. And 36 would just be 6 squared. There it is. Okay, so it was a circle. All this was a circle. It just looked crazy, crazy different. Okay, so find the center and the radius. Find the center. Center, no problem. X minus 1/2 would mean that my h part is the 1/2. And this is a critical part. This is why I like to write the equation at the top. X minus h, if I want h, that means I don't need the minus. The minus is part of the structure, not part of the h. So x minus 1/2 means I have x minus h, so h is the half. So, okay, h equals 1/2. What about k? I have y minus k. Here I have y plus 0. I guess that would be like y minus a negative 0. That works out okay, I think. Negative 0 is just 0. Okay, so k is just 0. K equals 0. Love that. And then r squared right here. That would be 6. Because it's 6 squared is r squared, so 6 is r. Okay, so there's a lot to kind of keep track of there. What are we talking about that's in the structure? What are we talking about that's actually the numbers? Okay, so find the center. Got it. The center would be at h comma k, which is 1/2 comma 0. Sketch the graph of the circle, or find the radius. Found the radius. Got that right there. So radius, here's my center. Sketch a graph of the circle. It's a lot easier to do it now than it would have been if I started trying to find things that made this all true. So now let's sketch it out. I have a center at 1/2 comma 0, so that means instead of taking one step over, I'll just go half a step over and no steps up. So that's 1/2 comma 0, and then I need to have a radius of 6. So that means that I've got 1, 2, 3, 4, 5, and 6, where I'm kind of jumping between the whole steps here. So 2, 3, 4, 5, 6, and I end up at the 6.5 mark for the end of one of my radii. And then that means I go 6 backwards over here. That would be negative 1/2 would be my first one, negative 1.5, negative 2.5, negative 3.5, negative 4.5, and then I think I'm missing one more. There you go, negative 5.5. So that would be the other end of my picture. And then I would need to be able to go down that amount too. That would just be 6 down. And then I would need to go 6 up. So 6 up would be right here. And I think all in all then, that would be the picture of my circle then. It's going to look a very flat circle. I'm not doing great through the online drawing here. But there we have it. There's a sketch of my circle. Doesn't need to be perfect, just needs to have everything that I need. Does it have any intercepts? Ooh, can't tell from the picture. Looks kind of rough. Oh, well, I guess I can tell for some of them. This one here, I've got an x-intercept at x equals negative 5/2. Negative 5.5. And then I have another x-intercept here at x equals 6.5, so I guess those are both x-intercepts. What about the y's? The y's are challenging. We might need some more space to do that one. What do we know about y-intercepts? Y-intercepts are when my x value is 0. I know that for sure, because if my x value is 0, then I'm just no steps to the left or right, so I must be right along this line. And so if x is 0, I'm at a y-intercept. Okay, I remember that part. So let's go back to our baseline. We can even use this expression right here. And let's put in x equals 0. So that would be 2 times 0 minus 1 over 2 squared minus 36 equals negative y squared. Okay, 2 times 0 would be 0, minus 1 would be negative 1, divided by 2 would be negative 1/2. So I have negative 1/2 squared. Minus 36 equals negative y squared. Okay, negative 1/2 times negative 1/2 would be positive 1/4. Minus 36 equals negative y squared. Okay, 1/4 minus 36 would be negative 35 and 3/4. Okay, equals negative y squared. Get rid of the negative on both sides by multiplying by negative 1. That gets me 35 and 3/4 equals y squared. I would probably want to make this all into one fraction instead of a mixed number. So let's see, 35 could be made to be over fourths if I multiplied it by 4. So that would be 140. I think it's 140. 140 plus 3 would be 143 fourths. Okay, 143 fourths. 3 fourths equals y squared, and then I get rid of the y squared by doing a square root of both sides. No, I get rid of the y squared by doing a plus or minus square root of both sides. Okay, so I do a plus or minus square root of both sides. Plus or minus square root of both sides. That causes my squares to cancel away, or my square to cancel away, and I'm left with y is equal to plus or minus square root of 143 over square root of 4. I guess I could just write that as a 2. Square root of 143 over 2. Oh, so those are my intercepts. I have all of my 4 intercepts. I could go over to x equals -5 and 1/2. I could go over to 6 and 1/2. I could go to y equals plus or minus square root of 143 over 2. So notice you have a bunch of different strategies here. The graphs will sometimes help us out. The sketches will sometimes help us out. Our logic will sometimes help us out. If all fails and it seems too difficult, you always have a back pocket rule, which is that if you want to find the x-intercept, just plug in a y value of 0. And if you want to find the y-intercept, just plug in an x value of 0. And then you just have to manipulate the symbols until you get what you want. So we've had a lot of fun with today's lesson. Notice that these are kind of puzzles. You really want to be exploring these and understanding what is that you can pull out for your future purposes. Is it a useful skill to be able to have memorized what the equation of a circle is and to be able to apply it somewhere? Maybe in some small circles and small cases, but if you allow yourself permission to explore into puzzles and really say, how do I tackle difficult problems and build up this resilience, and then after I've done all this work, how do I capture what I've figured out, and then how do I use what I've captured to make future problems simple, and how do I change my perspective depending on what would be an easier or a harder solution? These are the skills that you really want to be developing in mathematics. After all, mathematics was originally trained to kings and people of power, because it was believed to help take people to kings of moral leadership, as opposed to being what we're affectionately referred to as noble puppies. We're trying to grow all of us by practicing math from those who just simply settle for the things that are most apparent and easy to being thoughtful minds and asking ourselves constantly, how can I connect unrelated shapes? How can I express things in different ways? And how can I always be trying to make difficult problems simpler and easier to communicate to others?